Hi, in a previous video, which I'll link in down below at the end if you haven't seen it, and I'm sure you have because like 100,000 people watched it, seemed very popular, this Padauk, if I'm still pronouncing that correctly, Padauk 3-cent microcontroller that you can buy from LCSC here. I won't go through, but even in 300 quantity, under 3 cents each for a little 8-pin or a SOT23 package 8-bit microcontroller, not flash, but like one-time only programmable, but under 3 cents each. Remarkable. Anyway, one of the questions was from the video. After I did that video, apparently they completely sold out. There was nothing left on the website. But they do actually have more in stock. So a lot of people asked, well, was it just a one-time buy and stuff like that? It seems not. The LCSC have ordered more and stuff like that. Anyway, I ordered a bunch of chips. I've actually got them. They delivered, no problems. I actually got a whole reel of 10 cent or sub 10 cent or something 3.3 volt voltage regulators. Apparently they're pretty good. They sell really cheap voltage regulators, so why not have 3,000 of them? Beauty. Anyway, we've got the micros, and thank you very much to Padauk. Kindly saw my video and they kindly sent me the programmer. Now they say that it's only available from Taobao website, which is a Chinese like eBay type website, so it's not exactly easy to get. It's like $100 I believe for the programmer. They didn't have any of the programming adapters for them in stock, so they couldn't send me that, but I can just make one myself, no problems whatsoever. But they also kindly sent me the in-circuit emulator. I've done an unboxing on my second channel. Focus, you bastard. All right, there we go. In-circuit emulator for it as well, because these chips are one-time programmable. So obviously, like every time you compile your program and run it, you don't want to have to burn a new chip, right, and then plug it in and all that. So the in-circuit programmer allows you to run like it's not the real chip on there, but it emulates the real chip in hardware, and then you've got all your pins and you can connect it to your device under test. So this basically simulates the chip, and it simulates any of their size chips, any of their packages, because you can get them in much higher pin counts than this. Anyway, we're going to get this up and running. So thank you very much to Padauk for sending that in. Now, I just heard back from Padauk that they don't actually offer factory programming services, but they think you should be able to get that done at one of their authorized resellers. And as it turns out, LCSC are not, yet, I guess, an authorized reseller of Padauk parts, but that doesn't mean they're fake. LCSC actually buy them from an authorized dealer, which is Shenzhen Foresight Technology Co. And you go over to their website and, well, it's like, yeah, okay. I think you probably need to know Chinese to deal over here. But they do actually, look, they do actually have the ICE programmer down here. It's the same price as, the ICE. The in-circuit emulator is the same price as the programmer, and that's 460 yuan there. And what's that in Yankee bucks? That is 66 Yankee bucks for the programmer and the ICE. But of course, it's more expensive than that from other dealers. But that's one of their authorized dealers. So there you go. I've yet to find out if you can actually. I've asked LCSC, but they haven't gotten back. If they do, and you can actually get them factory programmed from them through the authorized provider, but supplied by LCSC, I'll update the description and leave a sticky comment down below. Because the value proposition for these parts always comes down to whether or not you can get them factory programmed. There's no point paying 3 cents for your microcontroller if you have to program each one, take it out and program each one individually in here. The time and money wasted, you may as well just, get the 40-cent microchip pre-programmed part straight from the factory. So, really, it all hinges on that in terms of viability for these types of parts. But, it's amazing that LCSC can sell these for under 3 cents, like in large quantity, 60,000, which is not a lot really in the in the mass volume scheme of things. 2.5 cents. Let's I call this the 3 cent micro, but really you can get it for less than that. That's like not even from the official distributor. So what are they making, like 1 cent each? You know, LCSC make their 1 cent, Padauk make their 1 cent, and their official distributor that that their LCSC are buying from, they make their 1 cent. It's crazy. So let's have a look at the software, shall we? I won't take you through the website, but if you go to the website, you can download, you can get the data sheet for these chips in English. So we've got the 154C, which we're going to compile for, but today we're only going to run it on the in-circuit emulator. I have to do another video for actually getting the real program, using the programmer, and then actually programming a real chip, put it on a breadboard and doing that. But if it works on the in-circuit emulator, we shouldn't have any problems translating, in theory, translating over that to a program. Anyway, everyone wanted me to see if I could actually get how easy it was to get a program running on these 3-cent microcontrollers with using like this weird looking IDE interface, which actually turns out to be quite nice. Anyway, you download it. It's like a 3 meg executable that installs 0.83 version for those playing along at home. It's the FPAA, which is a field programmable processor array. So it's kind of weird. And then we've got the writer. So once we've compiled it, I assume we can just write it. But we haven't tried that. So let's run this. It's a single exe. It's only 3 meg. And bingo, welcome to Padauk software. Thank you very much. And this is like just a change log or whatever. So let's go in and create a project from scratch. It's not easy. We still haven't found any sort of like processor architecture manual with all the instructions listed and stuff like that. So I've had to cobble this together, but it didn't take long to figure out all this, like an hour or two, tops to figure this out. So I cobbled it all together. Don't have everything fully understood yet, but we can get a LED flash in. So let's do it from scratch. New project. Okay. Now they use what's called Mini-C. This doesn't appear to be a thing. Apparently it's their own thing. Or you can choose ASM, for example. But we're going to do the Mini-C. So it doesn't look to be exactly, like ANSI C. It seems a little bit strange, but it's C-ish. Let's do a project called Togglebot, shall we? We can select our chips. So these are all the different chips that we can select. Well, let's do the 150C, shall we? Select device, PMS, PMC serial, AP serial. I'm not quite sure what that is yet, so we're going to leave it default. Now, frame, sysclock, IR, IHCR on 2. So these are the various internal clocks. We'd have to have a look at the data sheet. There's like the 8 megahertz economy oscillator. Is that like the low power oscillator or whatever? Anyway, if we choose sysclock equals IHRC on 2, we can get that working, and we can actually call up some help for that. There you go. They tell you executing IC under sysclock represents the most simple architecture which only needs to provide single easy frame. But at least we get it in English, right? Even if it is Chinglish. Anyway, it's actually got a surprising amount of help available for this thing. So actually quite impressed. So these are the different oscillator options. 1 key plus 10-second LED. There you go. Let's just get up and running with our program, shall we? So we'll leave that. The pin 5 here, PA5, port A5 pin can be an open drain or a reset pin. That seems to be common across all their chips. We'll disable the watchdog. So let's go. Oops. Found this bug before. You see, it didn't generate what we want. I think because I called up that help file. Oh! Right, so let's try that again. I won't touch anything else. Go OK, and bingo, we've generated our new template. And it includes extern.h, which is the header file, all the externals. This void FPPA0, that is like main. So think of that as main. They don't actually call it main, but that's what it is. So, as I said, not exactly standard C. And adjust IC, sysclock IRHC on 2. And look, there's open help here. You can move your cursor down here, and you can actually pop up the help. Look at this. Briefings, user who start the Padauk IC at first time might be curious about the instruction. This is great. This is like, they've really tried to write all this English help, and it's all there. I'm quite impressed by that. How do I shut down that frame? There we go. Got it. Okay, so it's generated our template. So we put our code in here like this. It's automatically generated an interrupt, but we can actually get this running. We haven't tried to delete the interrupt yet. Small step at a time. So you're basically following through as we're really learning with this thing. But this is our main. So we can type our code into here. Let's go. And here we go. We can, if we want to see what's in extern, we can go open document extern.h, and there's not much in there, is there? That's it. It's a bit disappointing. Get back. Anyway, so I'm going to put some code in there to define just a lead out, and that defines the port PA.0 and pin 0. So port A, port A, pin 0, I guess. So in while here, we'll just put lead out equals 0, lead out equals 1. So all we'll do is simply toggle a pin. That's it, and it'll just keep repeating in our while main. As I said, this is main. .c, as you might be familiar with in your regular embedded programming, and that should be it. We should be able to run that, although this interrupt routine, I haven't tried to take this out yet, so we can add a command just to disable interrupts, just in case. So there we go. We can go disgint. We just found that and copied it from somewhere else. So that's global interrupt disable. That's our code, and we should be able to now run that and compile. Let's try it. Now, our options up here, here we go, build. We've got rebuild all, we've got stop build, boom, and then we've got go. So let's just build it. Enable security, so we can actually, I didn't know it had a security bit. There you go. So we can disable security. Drive, low or normal. I didn't know it had variable drive on the output. That might be like drive capability, slew capability. So I don't know. I haven't read the data sheet in detail yet. I'm just running it. The low voltage reset thing, we won't worry about that. Boot up time, slow or fast? No idea. Let's just, by default it's set to slow. That's fine. Once again, I have not found any options. Oops, LVR is too low. Please refer to IDE help on LVR. I goofed it. Anyway, there's our compile. So I still don't know where the compiler is, what it's using, this mini C compiler or whatever. I don't know. I haven't looked into any of the details of that. But interrupt was not used. NB bypass. NB bypass. Great. LVR must be greater than 3 volts at sysclock IHRC on 2. Fine. We'll do that. So we'll set that to 3. LVR there. So we'll go back. We're all happy. By the way, I forgot to set up, you have to, the PA is the port and PAC is the control register for that port. So the output direction, we have to actually set up the output. If you want a pin to be an output or an input, you've got to set that up. So we've got to set lead out direction equals 1. So we'll just set that into our initial code at the start of our main before we hit the while loop here. Well, let's compile it, shall we? Let's have a look. Yay, 0 errors, 1 warning. Winner, winner, chicken dinner. Interrupt not be used and be bypassed. That's fine. I'm happy with that. So let's actually run it. Oh, by the way, there is a 9 volt input on this, but you don't seem to need it. It's powered from the USB. Great, fine. So we're not sure what the deal is there. We don't have a manual for this. We've got no idea. We're really running blind here. But let's run it. There is no indication of power or anything at the moment. So let's go to here, go. We found a bug in this. You've got to press go once like this. LVR equals, oh, popped up for a minute. And we get some nice stuff. Look at this. You know, we get like, it looks like register. That's the memory dump. We find it didn't actually run straight away. You have to go. You have to go. You have to enter go mode by pressing it again by the looks of it. So it's really strange. So let's do it again. Now it runs. We get a flashy thing. So now I'll hook up my logic analyzer to the pins and we should be able to see it toggle. So there you go. We'll just connect up to the first pin there, port A0 pin, PA0. Let's bring in my logic analyzer here. Start sampling. Ta-da! Winner, winner. chicken dinner. Our 3-cent micro is working, and that's how easy it is. And as I said, probably like within an hour of just dicking around, not even having proper manuals, we can get this to work. Oh, by the way, it's 2 megahertz, which is half as what it's supposed to run at. We found something that mentioned that the ice potentially runs at half the speed. So I still like, that's what they say. So anyway, yeah, so I think it's maybe it needs to do its icy stuff in the background and whatever it is. Anyway, it recommends that you run the processor at twice the speed to what you actually need. But there it is, it's toggling. We've got a pin toggle at 2 megahertz. It's not a 50% duty cycle because it needs to do its it needs to loop back or whatever. Now you might actually notice something interesting up here. Look at some of the gaps between, look, the duty cycle of these is actually different, right? It goes to 2.4 megahertz, 2 megahertz, 2.4 megahertz. What's going on? Well, this is actually a trap for young players with timing analysis mode on logic analyzers like this, Sadly logic analyzer, but any logic analyzer. Basically, it's because we're trying to measure a 2 megahertz signal at a 12 meg sample per second rate here. So if we actually go higher than that, 24 meg samples per second, it's because we don't have the temporal resolution to actually always get a correct, accurate frequency on there. So really 24 meg, we'll still kind of see it. So we'll sample now at 24 meg, but you'll notice that periodically it's showing these sort of like it changes the duty cycle like that. And that's just a nature of the sampling, and it'll get worse the lower your sample rate goes. So if we go down to say 8, it should be like really terrible, Muriel. Well, it's different. Yeah, anyway, look at that. I mean, well, in fact, look at that. At 8 meg, there's whole sections where there's just nothing there. So just be careful of that when you're using your logic analyzer. So even at 24 meg samples per second, there will be, like, it'll show you like 2 megahertz everywhere on both of the different duty cycles here, but there'll be one point where it switches over there, just gets out of whack a little bit. There it is, 2.182 megahertz. So that's just the sampling resolution that we've got here. But it tells you it's 2 megahertz in here, and it tells you it's 2 megahertz in this section here as well. So you know that's right, but just that little changeover point. Timing mode, sampling rate, it's a big deal. And the good thing about once you've actually compiled this is that you can actually like hover over your variables and stuff like that. It shows you your stuff. You can hover over, say, port A there, and you can right click on that, and you can go to definition of port A. And there you go, you can jump over to where it actually defines port A in the, does it tell you what file? Inc. Yeah, there we go, PMS150C Inc. So that's the include file. Please don't change the following code. It's only used for internal engineer. I love it. This is great. So there you go. That's the include file that sets up all your, your registers, your ports, your timers, and there's TM16, for example. So we have that here. Interrupt. Go to definition of interrupt queue. There you go. So it's all there. It's pretty cool. But that's all it took. Really, there's a bit of learning curve there. Maybe we got a bit lucky in, finding things easier than what other, if you're having a bad day, Murphy's over your shoulder, you may not be able to have found all this stuff. But anyway, that's pretty groovy. I like it. It worked. A treat. Now, why do we have to do IHRC on 2? I'm still not. Can we go like divided by 1? Can we do that? Let's just build. Let's just build. Nah. Didn't like that at all. Wasn't a happy little camper. But anyway, we still don't know why you've got to generate, why you've got to go. You've got to go. It looks like it sort of like stops at the start there. Maybe it's like, it looks like maybe it's in breakpoint mode, or like a single step mode or something like that. And yeah, I'm not sure. It's literally the first time I've used it. Okay, now we've got a basically the same thing here, but what we're going to do is we're going to use the timer. So T16, so 16-bit timer here, and we've just got some extra code here. Oh, I've got to take this out. I was just dicking around here. A code which will use our timer here, and now it will toggle our pin slower. Hopefully, we'll get a 1 Hertz square wave out of this thing. So we haven't figured out like delays and stuff, like any sort of like delay routines and stuff like that we've got. So we're just using the timer. There you go. So interrupts not being used, it's just warning us. We use 4 memory. Remains 60 unused memory. So we're using 4 bytes of memory, or 60, 4 words of memory, and we've got 60 unused words of memory left. And ROM size for the 160 last year's code. Remain free. There you go. Plus 358 hex for those playing along at home. Do your conversion. Anyway, let's go gadget. Let's go back to our Saley logic analyzer here. Taking 10 seconds worth of data now. I'm a bit overkill on the data there, but there you go. It's 1.003 hertz. Of course, internal RC oscillator, so it's not going to be absolutely precise, but good enough for Australia. Like, 3 millihertz out. I'm pretty happy with that. So there you go. There's there it is. We can toggle. And that's all there is to it, using the timer thing here. And once again, like, I haven't tried to look at, haven't single stepped, I haven't done, set breakpoints or anything, fancy at all. Just wanted to get a LED flasher up and running, but I know you want to see a LED flash. Okay. Hold the tongue at the right angle. Please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. But there you go. We have our flashing LED. Woohoo! Our Blinky. We got the Blinky. Winner, winner, chicken dinner. So there you go. We actually used this thing without too much mucking around. There was, a bit of going, I don't know, try this to get it up and running, cut and pasting examples. They do have examples, by the way. They've got some demo projects, but none of them are the processor that we're using, I don't think. But yeah, let's have a look at stop, sys, T6, so timer 16, key, LED, ADC, get VDC, GPC, they've got some, I don't, PWM, there you go. So maybe we can open up PWM project and have a look at this. So, they've got some example code which you can copy, and it seems to be their own mini C, whatever it is. It would have been nice if they just written it for support for GCC, for example. That would have been great, So I don't know why they did that, but somebody could easily write a GCC thing, couldn't you, David? Yep. How long do you think it would take you to write a GCC port? Padauk.
3 weeks.
3 weeks. There you go. 3 weeks.
A partially broken one.
Partially broken GCC port.
Yeah.
But there you go. We were able to get to Blinky with not much trouble at all. Granted, we had the in-circuit emulator. The next step will be, of course, the programmer. So this will be a part 2 video where we'll program the chip, make a little programming adapter for it, but I'm sure it works. The writer program, haven't even loaded up OTP writer. There we go. So load file, don't even know, auto program, rolling code, is that serial code generator? Whatever. Anyway, it works, and their interface is actually surprisingly good. It's got color syntax highlighting, it's got context sensitive stuff. Their help seems, surprisingly comprehensive, considering that there's not that I've found, there might be a processor manual or whatever that lists all the assembler code. Haven't done assembly yet, still not sure what the deal is and all that sort of stuff, but this mini C, they call it, we're able to get something running. And some people may go, well, I wouldn't trust this thing at all. Like some, obscure Taiwanese company making their 3-cent microcontroller with their little 3 meg IDE using mini C and non-standard stuff. I wouldn't trust it at all. And, well, fair enough. But at the end of the day, if it works and you have use for a 3-cent in fairly lowish volumes, only 300 plus volumes, 3-cent microcontroller, if you can program the things then you know, like, and it works, and you can test and verify that it works, and you can still get them from LCSC. They keep them in stock by the looks of it. I have asked them if you can actually order these pre-programmed. They're still getting back to me on that. So maybe I'll update you in the next video. I haven't heard back from. Might give them another poke. Pun intended, because we're talking about programming. I'm here all week. So yeah, like the value proposition, if you can't get these programmed, and you know, and if this is your only programmer and you need to program 10,000 of them, it's kind of going to ruin your day and takes away the value proposition of the 3-cent micro. So so the value of these in volume hinges on the fact, well, hinges on whether or not you can get these pre-programmed from the factory. If you can, that's killer. You can simulate your code on the ice, and you can actually get it running. You can experiment, and you can, you know, do all sorts of stuff. Then you can program it. You can verify your code. These micros only can, you know, very small programs on these, so it's not hard to. So you could like verify a complete micro. You can test it over voltage and temperature, and you can qualify these things yourself. It's not necessarily difficult if you have the means to do it. And you know, there are people who will say, well, you know, just go for a 30 or 40 cent or whatever. I think it's 40 cents for the lowest cost pick that you can order pre-programmed from the pick factory. It's got industry standard support, etc., etc. And well, you know, yeah, that's a valid argument too, but 3 cents. I just love it. It's great. There's got to be niche uses for this. This is fantastic. Anyway, if you like the video, please give it a big thumbs up. And if you want to see us program stuff and things like that and get something running, and we're thinking about, now that it's all working and we see, I'm sure we'd be able to program this thing. Shouldn't be too much effort. Thinking about a big project that needs, like, you know, 10,000 of these things. That'd be great. Somebody actually bought up 10,000 of these. After I did the video, somebody went and purchased like 10,000 of the SOT23 version or something. Anyway, I've got the SO8, I've got some SOT23s, I've got some other variants of it as well. So yeah, you might be able to do some interesting projects. Anyway, comments down below. Catch you next time.